Welcome back. We were discussing the bipolar junction transistor biasing. We covered the fixed biased and the emitter bias. Also, we discussed the voltage divider bias. Let us take the discussion forward with collector feedback configuration. So, in the collector feedback configuration, an improved level of stability is achieved by introducing a feedback path from the collector to the base. So, if we see the circuit, so here in BJT biasing, between the collector and the base, there is a feedback resistor which is added, and this feedback resistor will improve the stability of the BJT. The Q point will be less sensitive to the variation of the beta and the temperature changes than other biasing methods. So compared to the previous biasing methods like the fixed bias, emitter bias or voltage divider bias, the collector feedback configuration is less sensitive to beta variation because of these feedback resistor which is connected between the collector to base. So if we do the analysis from the base emitter loop, so we can write down the KVL equation where the collector current IC dash will be split into the collector current IC plus the base current IB. So now the collector current which is IC dash is splitting up with two different path because there is a path which is splitting this collector current. So in the KVL equation which we have written for the base emitter loop, we can have with an assumption that the total collector current is approximately equal to IC dash. Also the collector current equation is given by beta into IB. The emitter current is approximately equal to the collector current. So the KVL equation can be improved in respect of the collector current and the base current. So we can rewrite the KVL equation and find out the base current from the KVL equation. So the new base current, whatever we get for the common collector configuration, we can deduce some conclusion. Let us see. So here we can write in general form the value of the base current as V dash by the summation of RF and beta R dash. So what we have discussed that in the fixed bias configuration, the term beta R dash does not exist. So this is 0. Whereas in the emitter bias, the beta is equal to beta plus 1 and the R dash is normally equal to the emitter resistor. So in the common collector configuration, we can say that the collector current, since it is beta times the base current, so the collector saturation current ICQ can be written as beta V dash divided by RF plus beta R dash. Now if we arrange this in terms of beta, so the beta can be cancelled out and take with respect to RF. We know that R dash is very greater than RF by beta because beta value lies between 50 above. So this value will be less and hence we can say that the collector current saturation is V dash by R dash. So it is independent of any beta. So there is no role of beta variation in the collector current. When we do the analysis in the collector emitter loop, so we can again write down the KVL equation in this collector emitter loop and we can improve the equation considering that IC dash is normally equal to IC and the emitter current is equal to IC. So the KVL equation can be improved and rewritten in a better format. We can also obtain the collector to emitter voltage which is equal to VCC minus the total drop due to the collector resistor and the emitter resistor. So this is exactly the same as the emitter bias or the voltage divider bias. The next configuration that we'll take is emitter follower configuration. We have seen that in collector feedback, the output voltage is basically taken from the collector terminal. Now in the emitter follower, the output will be taken from the emitter terminal as the output. So the output what we are taking is from the emitter terminal. And the DC equivalent of this network, if we see, so we can remove this capacitor with open circuit and write down the KVL equation in the DC equivalent network. which is this one. And we also know that emitter current is beta plus 1, the base current. So if we again substitute this in the KVL equation and rearrange the equation, so we get the base current equation is this one. Output network equation of collector to emitter voltage is equal to the emitter voltage minus the drop in the emitter resistor. The last configuration that we will discuss is basically the common base configuration. Here we can see that base is common between the input and the output terminal. So the input signal is connected to the emitter terminal and the base is held at ground. So we have the base to be at ground and or just above the ground potential. So it is closely to 0 volt. The common base configuration is unique in nature due to the use of two supplies. So we are using one, the emitter supply, and another one is basically the collector supply. And it's designed where the base is the common terminal. So base is common and we are using two supply, one from the emitter, another from the collector. The advantage lies at low input impedance, high output impedance, and a good gain. And if we do the DC equivalent analysis of the common base circuit, so we can write down the KVL equation first and obtain what is the emitter current. On the other hand, we can also obtain the collector to emitter voltage and collector to base voltage with writing the KVL equation. Assumption is emitter current is approximately equal to the collector current, and substituting this in the KVL equation, we will get what is collector to emitter voltage. Collector to base voltage we can obtain as the drop across the collector. We take it out from the collector supply, and collector current is normally equal to emitter current. So we can also get the collector to base voltage, taking the drop across the resistor of the collector from the collector supply. So all the configuration that we have discussed, the first one is basically the fixed bias, second one is the emitter bias, third is the voltage divider bias. So we can write the pertinent equations and the configurations. We can see where the fixed bias will be at ground potential with respect to emitter. Here we are connecting the emitter resistor. The voltage divider bias will have the two resistors R1 and R2, which will divide the voltage. In collector feedback configuration, we are having a collector feedback resistor. In the emitter follower resistor, we have the configuration where we are treating two supplies and the input is taken at emitter. Common base configuration, we have the base as common and two supplies we are giving, one at the emitter, another at the collector. So all the pertinent equation we have discussed how to put it in the form of KVL and KCL and do the derivation. So this complete the discussion on BJT, and next topic we will take on amplifier. So how BJT would be acting as an amplifier. Thank you for now.